So hello, in this lesson about wireless networks. My name is Andris Igaunis, and in this lesson we will study about wireless networks, wireless networking, and how we can use it to our advantage. First, I want to talk about the things that you will be able to do at the end of this lesson. So you all are studying electronics engineering. So you will become engineers. You will be the system designers or at least implementers. So you need to understand different kinds of wireless networks, their advantages and disadvantages, and maybe how to tweak them in such a way that they work best for your case. For example, if you want to send a little bit of data in short distances, you would want to do it as fast as possible and you don't care about long distance data transmission. If you want to send data over long distances, the parameters for the network will be completely opposite of fast data transmission. And we will study about how these two things change each other and how to tweak them to your particular use case. We will also study about how exactly Wi-Fi, Bluetooth, Z-Wave, and Zigbee and other wireless networks work, and what they have in common and what are the differences. And you would ask yourself, why should you study this subject? Well, if you want to become electronics engineers, you should know as much as possible about electronics, because then you can earn more money. If you're smarter, if you only know wired electronics, well, then you have less opportunities in life. If you know wired and wireless networks, you can have so many more job opportunities, career opportunities, and you will, of course, make more money because you know more than some other people. So, you know, if you want to make a lot of money, please study this subject and use the knowledge. So, I personally, I have worked with wireless networks for many years now. I think it will be something like 9 or 10 years already, mainly in smart home area, but also in telemetry and remote control of devices. So the last place where I worked that was about wireless networks was a company named Sia Istabai. I will show their webpage and you will understand what I'm talking about. So our company designs and sells smart home devices. So I'll just go directly to shop because you're interested in what kind of devices we have. So we have a base station that collects data from sensors, and you set some settings. For example, you want to set the room temperature, and base station checks out the room temperature from temperature sensor, and it makes a decision to switch on or off the radiator. So we have these wired valves or wireless valve control units, and basically the base station opens or closes it depending on the temperature. You know, a simple control of room temperature with on-off switching. So in this case, because most people have already built the houses, all of the connectivity has to happen wirelessly, because you don't really want to draw a cable from your radiator to the base station and then back to the temperature sensor. Your room would be full of wires. You don't want that. You want wireless communication that is simple, that is robust, strong, and that just works. So we will look at how to build such thing. We also have built wall plugs. You can switch on and off an electronic device, for example, electrical radiator, or you can use it as a home safety feature. You can plug a lamp inside of this wall plug, and you can remotely switch on and off a light in your room. And for example, if you go away from your house, if you leave, for example, for 2 weeks going on a trip, the thieves that want to steal some stuff from your house, they usually first check that nobody is at home. They watch your house for several weeks, maybe for several months before they break in and steal your stuff. They check out at what time you leave, at what time you come home, and they do it by looking at the door when you go in or go out. They also do it by looking at the windows. If the house has lights switched on, it means that somebody is at home, and the thief will not try to break in, because thieves never want to get caught, because if they break in and you are stronger, then you can beat them or catch them. And even if you are weaker than a thief, thieves don't really want to kill someone, because stealing is a small crime, it's non-aggressive crime, penalties are not that big. But if a thief breaks into the house and is surprised by a person living there, and they start a fight and the thief accidentally kills the person living in the house, it's totally different story. You get lots of years in prison, so nobody really wants to do that. So thieves always make sure that nobody is at home. So if you have some technique to remotely turn on a light in your house, a thief might think that somebody is at home because somebody just switched on the light. So the thief will not enter your house. So using these wireless data transmission and wireless devices, you can do some kind of safety stuff in your home. So this base station, for example, just like in any smart home network, base station is connected to the internet. So you can use your phone that also has internet connection, and you can remotely control the home or switch it on and off. So this thing is really perspective, and more and more people start to use it. So this would be a small network that many companies are building. So this product isn't really that unique. We started building these devices 7 years ago, but now many companies build these devices. So you can just shop around and check out prices if you want to buy, and you will just buy from the cheapest. So my job was to build electronics that are inside of these devices. So if you break this case open, there will be PCB with some components, with antenna, with battery and connectors. So my job was to design that, and also to set up the wireless network, to send some settings to this wireless network so that base station and temperature sensor hear each other and work over the longest distances. We will study these things in this course. So in this course, first we will look at how exactly radio waves are transmitted and received, what are the settings of the wireless link. Then we will look at how the bits are sent forward and back. Then we will study how packets are routed, because, for example, if you have a base station and temperature sensor is really far from the base station, but there is, for example, a wall plug in between, the wall plug could be used as a retransmitter, so the temperature sensor cannot reach the base, but it can reach the wall plug, and then the wall plug forwards the packets to the base station. And we will study a couple of algorithms how we can route packets in such way that they reach the destination. There will be some complicated ways and also some very simple ways that anyone can build. Then we will also look at wireless network security. So the problem is the following. The first wireless networks had no security at all, but they really didn't need any security because 99.9% in this planet don't understand anything from electronics. So even though there's no encryption between, for example, motion sensor and base station, nobody can really do anything because humans cannot hear the electromagnetic waves or interfere with them directly. You know, you can only see a small spectrum of electromagnetic waves, which are not even used here. So, you know, even though there's no encryption, most people cannot really interfere with the signal. But as time goes by, some electronics engineers decide to become hackers, to become evil guys that try to interfere with the connection and to change it in such a way that they get some information that they can use to steal stuff from you. Of course, in the last 3-5 years, everybody is starting to implement security features in this connection. It's wireless, and the problem with wireless connection is that radio signal goes in all directions. So the temperature sensor sends the signal, but it doesn't go directly and only to the base station. It goes to all sides. So on one side, there's a base station, it hears the signal, but on the opposite side, there might be, for example, a hacker listening to the transmission, and he also hears the information. So radio waves go to all directions. So anyone can hear any messages if they're close enough. So you would need to encrypt them. I will give you a use case. Let's say we have a motion sensor and there's no encryption. So when the motion sensor detects motion, it sends some information to base station saying, hey, there is a motion. But when there's no motion, this motion sensor, for example, doesn't send anything. So if somebody wants to get in your house and steal your stuff, they can just listen to this motion sensor. And if motion sensor stays quiet, it means that nobody is at home. At the same time, if the thief has some receiver that hears that motion sensor is saying something, for example, movement detected, then the thief knows that somebody is at home, somebody is moving. So we would know that somebody is at home and we should not enter the house and should not try to steal something because we will be caught. So we want to encrypt the messages in such a way that motion sensor occasionally sends some information to base station saying there's no motion, right? So, you know, the motion sensor is sending information whether there is motion or not, and the messages motion and no motion should be indistinguishable from for the hacker who hears them. So we want to encrypt them in such way that even though hacker hears the message, he cannot understand whether the message says that there is motion or that there isn't motion. And we will study about it as well. So you will know how it's done. So who should study this subject about wireless data transmission? If you want to use wireless devices in your life and you want to understand how they work, if you want to understand what range you can expect with them, you should study this course. Then you will just be a smarter person, you will understand how they work, and you will be able to design your own wireless network, or you will be able to build devices for an existing wireless network. However, if you are not going to be an electronics engineer or system designer, maybe this course isn't for you, but then you wouldn't be studying in university. So I assume that you want to learn about wireless data networks. And so to successfully complete this course, you need to do 3 very simple things. First, you should connect to the lessons and listen to them. And if you have some questions, you should ask the questions in the chat and I'll just answer to you. I'll try to explain them to you. So just visit the lessons, be online, listen to them, and you'll be fine. Second thing is I will put tests and some very simple tasks in Artus that you need to do usually every 2 weeks. There should be a new test in Artus, and you should fill them as quickly as possible, because by the end of the semester you might not be able to remember some things from the beginning of the semester. And if you listen to the lecture and also do the tasks, do the tests, you will remember them much better than if you don't do them and then you try to do them several months later, not remembering anything and making a lot of mistakes. So about the tests, you can do each test only once, or you can do it 100 times. I don't care. You can try to do the test as many times as you wish, because the goal of test is not to punish you, it is to invite you to learn, so to educate yourself. So you go to the test, you fill it once, you see which things you got right and which you got wrong. The things that you got wrong, you can revise, check out, and study a little bit more. Then you try to do the test the second time, and hopefully the second time you have no mistakes and you have 100% correct answers, and you can be happy with the high mark. So the second part is the tests in Artus. The third part is work in lab. So every other week we will meet in university. I will register you and you will do some experiments, some programming with development kits that use wireless transmission, and you'll just, just play around with wireless networks a little bit. So you understand how they work, you can touch them, feel them, and program them. So that is the plan. And hopefully by the end of semester, you will have visited most of the lectures, most of the labs, and most of tests, and you will have high marks. And in that case, you will not have an exam. You will have an automatically high mark. However, if you don't study, if you don't show up, I cannot give you a mark, and then you will need to do an exam, which you will most probably fail because you haven't studied anything, right? So the easy path is to just do everything during the semester, and we have 16 weeks to study. So this is the second week. Maybe you will have one extra lesson at the end of the semester to fill the last week, but maybe we will just revise everything faster during the lectures and you will not have this one extra lesson because you will have studied everything else faster. And so we should only spend 16 weeks studying this, and the last 4 weeks will be free for you if you have done all the tests, all homeworks, and all labs, right? If you haven't, then the last 4 weeks of this semester will be very hard for you. So let us start to study about wireless networks, how they work. So I will use this program to draw some information that you will hopefully find interesting. So how do wireless networks work? What makes things become wireless? So if you have studied electronics, you know that, for example, let's say you have a battery and you attach it to a light bulb. Right? So there is some current that flows, and there is some voltage across the bulb and across the battery voltage, right? In this circuit, nothing really happens, right? Because it's a DC circuit, and DC signals don't make any kind of electromagnetic waves. So this is not what we're going to study very much. However, the first electronics engineers knew only DC circuits and they used only those. And only later people started experimenting with AC. And we will talk about high frequency AC signals. So instead of DC battery, you have some AC source. And if you have some kind of coil and some kind of capacitor, you get the following thing. So the coil, there is some current that flows through the coil, and the coil makes magnetic field. So the coil creates magnetic field. We will call it H. Magnetic field. Capacitor has some voltage across it. And inside of this capacitor, we have electrical field, voltage. And you have probably studied electrodynamics before, so this will be just a reminder. If you have high frequency, even a trace on a PCB can become this L and C. And if you open up this capacitor, so electric field is in this way, and magnetic field is probably in a coil in this circular way. So if you take a generator and make an antenna out of it, you know, just cable, just some metal conductor here and metal conductor here, and you go to high frequencies, you have electrical field from top to bottom, which is changing. And you also have magnetic field, which is around these wires. And as a result, you have magnetic and electric field, and these fields have this property that if they're perpendicular to each other, you get that this thing starts to radiate to all directions. So energy starts to go outside of this circuit into the air, and you calculate this energy by multiplying. This is actually power. Pointing vector is E times B or H. I guess H. So at low frequencies, nothing happens, but at high frequencies, things start to radiate. The energy, I would say, hops off the circuit and starts to travel in free space in all directions. And you get electromagnetic waves that go outside of the circuit. And you can have a second circuit, which also has an antenna and some kind of sensing device. And if it's tuned correctly, this antenna catches some of the waves and it starts to sense the signal and shows the same signal on its output. So first thing that has generator is a transmitter, and second part is a receiver. So electromagnetic wave starts to resonate inside of this antenna, and it receives the signal, it senses the signal. The signal is very weak, but you can sense it, you can amplify it, and you can hear it. So we have high frequency source, which starts to radiate electromagnetic waves, and they can be heard with a receiver. So now we need to talk about the frequencies that we can use to radiate. As I said, this is AC signal, and AC signals have a parameter little f frequency. Okay, so we would first need to talk about what frequencies do we consider to be able to radiate. Actually, 1 hertz frequency doesn't really radiate. You have 50 hertz in your wall socket, and it's also very low frequency, it doesn't really radiate. In modern days, the frequency that is used for example, Wi-Fi is 2.4 gigahertz, which is high frequency. So let's see. I will make it in a new page. So the wireless signal has the first property, frequency. We will call it F. And usually it is hundreds of megahertz, gigahertz. And for wireless sensor networks, we have the following rules. You cannot really transmit in any frequency because some frequencies are used for airplane communication, some frequencies are used for radars, to sense, for example, airplane location in the air, and some other frequencies are used by military, and you definitely don't want to use those frequencies. So people have agreed that, for example, for wireless sensor networks, you have only a limited amount of frequencies that you can use. So, for example, in Europe, you have to choose a frequency from the following set. Well, I'll just write the most popular ones. So in Europe, you can transmit signals at frequencies, for example, 433 megahertz, 868 megahertz, 2.4 gigahertz, right? All other frequencies are forbidden. And because there are only few frequencies that you can use, you can only use them for a short period of time. You cannot constantly transmit some information at 433 megahertz. You transmit it, and then you have to be quiet for a certain time. So you need to also take notice of that. So in America, the frequencies are different. You have 315 megahertz, 915, or 928 gigahertz. Okay, all right, 915 megahertz, and also 2.4 gigahertz. And reason is the following. These radio transmissions were started in 1950s, 60s, 70s, and during that time, there wasn't really any internet. So United States of America partly accidentally selected 315 megahertz and 915 megahertz. Europe semi-accidentally selected 433 megahertz and later 868 megahertz. And only later, when modern day Bluetooth and Wi-Fi devices were invented, both of these territories or areas or continents decided, okay, first 2 times we missed, now let's select the same frequency so that the same devices work both in Europe and in USA. And thanks to that, in Europe and in USA, Bluetooth and Wi-Fi routers and devices work interchangeably. However, for example, older TV remotes, car remotes, and other sensors don't work in one location if they work in the other. For example, you buy some Z-Wave devices that work in Europe 868 megahertz. In USA, you cannot use them because you would be using a frequency that is forbidden in USA. In USA, you can only use 315 and 915 megahertz. Okay, and you can check out other locations in the world. You can just do a Google search. So these frequencies are called ISM bands. It is short for industrial, scientific, and medical bands. We are using only this industrial. Scientific is a little bit different thing, and medical is a little bit different thing, but generally these are all called ISM bands. And you can just check them out in the internet and see the values in different locations. For example, ISM band in India. Let's check out. So 2.4 gigahertz, you know, these new routers, which are 5 gigahertz, here is their band. What other bands do we have? Here's an article in Wikipedia, and I think it also had some information about it. Frequency allocation. So again, this information is not complete because some locations have one rules and some other locations have different rules. So you would need to dig a little bit deeper. But as far as I remember, for example, India has the same bands as Europe. So in India, it's 433 megahertz, 868 megahertz, and 2.4 gigahertz center frequencies, or just shorthand frequencies. So you can use these. So let's talk about, you know, the difference between these options. So one frequency is lower, the next one is in the middle, and the third is high frequency. So 433, 868 is approximately 2 times higher, and 2.4 gigahertz is approximately 4 times higher than the previous one. So the difference is pretty significant. Why would you want to choose, for example, 433 megahertz or 2.4 gigahertz? Well, first reason to select one of these frequencies is 2.4 gigahertz devices work internationally. So if you select in your wireless network 2.4 gigahertz signal, you know that you can sell the device in Europe, in America, in Canada, in India, Australia, wherever, and it will be legal to use it in those areas because the entire planet has decided that 2.4 gigahertz is a good frequency to use and legal frequency to use. However, there is this property of electromagnetic waves that the higher you go in frequency, the lower range you have. One of the reasons is that, for example, these microwaves, 2.4 gigahertz signal, is absorbed by water. Low frequencies go through materials better, but higher frequencies get stopped by objects, especially objects that are containing water. So microwave signals are not that great in rainy days. So low frequency goes through object. I don't know, let's draw a human. So this is a human. Human consists of water, of some material. Low frequencies go through. High frequencies are absorbed by objects, by walls, and by people much better. And so high frequency signals don't go through material that good. Okay? So if you want your signal to go as far as possible, you would want to use a lower frequency. Okay? And as you have noticed, there is these widespread lies about how new 5 gigahertz routers are so good, they are in higher frequency, so you get a faster internet connection. But actually, their range is much smaller than the 2.4 gigahertz. So 2.4 versus 5 gigahertz Wi-Fi. Theoretically, 5 gigahertz Wi-Fi uses directional antennas, so it should aim at things better. But in reality, its range is just much smaller because it's higher frequency, and higher frequencies get absorbed by material much better. And also, you would agree that air also has some resistance, and higher frequency signals don't go through air even that much, well. So high frequency international, low frequency is higher range. Okay. So next thing that we need to talk about is the volume or the loudness of the signal. So the second parameter that we will talk about is loudness of signal. We will call it P because it's power. It has 2 units. In wireless networks, in wireless sensor networks, we will have the following units, usually milliwatts, I'll write it like this so you understand. And the second measurement is dBm, decibels to milliwatt. Decibels to milliwatt. If you work with radio signals, you need to understand both concepts, milliwatts and also dBm, decibels to milliwatt. Let's start with milliwatts. Milliwatts is pretty straightforward. You know, it's just transmit power. So you have a generator. Let's say you have a transmitter. Where will we put it? We will put it right here. You have a transmitter. You can buy transmitters in the internet, but we will talk about more. We will talk about these transmitters more later. But for now, it's just a box that we will call transmitter, TX. TX means transmission. And it has an antenna. And you can transmit power. You can transmit your signal, but you can transmit it in a very loud manner, or you can transmit the signal in a very silent way. So this thing needs to be regulated. Of course, if you use a very, very loud signal, the signal will travel much further away than, for example, a very weak and silent signal, right? That's common sense. So let's say you use a very strong, very loud, very high power antenna and transmitter. The good thing is you will have a very strong signal at the receiver, right? So this is good. Receiver we will call Rx. But the problem is that if you have extremely loud signal, maybe there's another transmitter for another network that is trying to transmit also. Maybe there's another receiver that wants to hear its transmitter TX2, but because your signal is so loud, the RX2 receiver 2 doesn't hear the receiver TX, the transmitter TX2, because your signal is really, really loud, and these two devices cannot communicate. So TX2 wants to talk to RX2, but it's impossible because your loud transmitter is interfering. You have a good range, but other devices suffer. For this reason, to avoid the situations where somebody just buys an extremely loud and strong transmitter, uses the network, is happy, but everybody else is sad, there are limitations on how loudly you can send the signals. And for example, and these powers also, the rules are for different frequencies a little bit different, but I'll just write them down. So in European Union, if you want to transmit a signal at 433 megahertz, maximum transmit power is, I guess, 10 milliwatts. Milliwatt. Let's see. I guess something like this. For 868 megahertz. Well, because 868 megahertz is higher frequency, so it would have a lower range. When people decided to start using this 868 megahertz band, they said, okay, the frequency is higher, so the range will be a little bit worse because material will absorb these signals a little bit better. So we have to have the same range as older 433 megahertz devices. We need to increase the loudness a little bit. So maximum transmit power for 868 megahertz devices is 25 milliwatts. And for 2.4 gigahertz routers, I think that they can transmit at approximately 100 milliwatts, maybe even more. So one reason for routers to transmit at 100 milliwatts is because we want a better range for our Wi-Fi's, and also because 2.4 is absorbed better by materials. So to compensate for that, we need to send a little bit louder signal. So now, you know, otherwise some company would buy a transmitter that transmits at, for example, 120 watts very loudly, and all the devices that transmit only at 10 milliwatts, their signal is so much more silent that nobody would hear them. So this is forbidden. You have to limit the loudness of your signal to these powers, depending on frequency. In United States of America, these powers are a little bit higher because historically USA was relatively rural country with lots of agriculture, and many houses were very far from each other. So to compensate for that, they right from the start allowed louder signals to be transmitted to go across the fields and greater distances because they were spread more apart. In Europe, it's a little bit different story. So this is the maximum power. And if you buy a transmitter, you can tell it how loud it should transmit. You can tell it, okay, so for example, work with 5 milliwatts instead of 10, then you are 2 times less loud, so you don't have to worry about interfering and bothering other devices, right? So this is the signal strength. And another thing about these powers is, as I mentioned, uh, the microwaves are absorbed by human body. So we don't really, if we use the very, very strong transmitters and they go through our bodies, we would heat up like in a microwave. We would absorb these waves and they would increase our body temperature. And people are pretty scared of it because nobody really knows the implications of that. Some people say that these waves also can hit our DNA and we can start to have cancer from this energy. So this is another reason why these powers are so small, right? It's only, 25 milliwatts, you don't even feel it. 100 milliwatts, very, very small power, because we don't want these waves to, heat up our bodies, change our brain and stuff like that. So there is still research going on because people are pretty scared. There are many people who are scared of, for example, 5G signal, because they think that these high frequency, high power electromagnetic waves from these new LTE and for 5G towers go through human bodies and, cause cancer and other diseases. But actually, well, first of all, the power is limited. And secondly, there isn't really any convincing evidence that these waves would really cause all of those diseases, because the frequency is relatively low. The waves that do impact DNA are X-rays. But if we check out the spectrum, let's see, electromagnetic wave spectrum. For example, in this picture, visible light is, for example, in this graph, it's not very precise, but generally it's in the middle. Before it is infrared, radar, FM, TV, shortwave. So we're working somewhere here at shortwave, actually a little bit higher, a little bit above these FM radio waves. Wavelength of, for example, 868 megahertz is 35 centimeters. So we're approximately here, right? So these waves that we are using in wireless sensor networks are approximately here, and the really dangerous gamma rays and X-rays that really cause cancer and are generated through, for example, radio active materials, is all the way across the visible light on totally different side of electromagnetic spectrum right here. So, there's a high probability that it will turn out that these radio frequency waves are actually not dangerous at all. Maybe only at very high powers where they heat you up significantly and your brain boils. But otherwise, it's very unlikely that these waves really cause cancer, because cancer is caused by these high frequency, high energy waves, X-rays and gamma rays, also a little bit by ultraviolet rays. But we know that, for example, visible light doesn't really cause cancer, and these frequencies are even lower. So, science should, of course, check out all the possibilities, but we should not like sweat in fear and be afraid that we get cancer from these 868 megahertz or 2.4 gigahertz, because compared to the really dangerous waves, they're really, really low frequency, right? So until medical people prove that these are dangerous, we should just live peacefully with them and use them without fear. And for example, frequencies that are used in cell phones, they are approximately 2 gigahertz and 1 gigahertz and 750 megahertz. So they're not really that much higher than 2.4 gigahertz. So, you know, that's about the power. So, okay, I will delete this part. And maybe a couple of words about the cell phones. So, the resultant distance of 433 megahertz signal at very low frequencies could be, for example, 5 kilometers, right? But at very low data rate. I'll put asterisk. 868 megahertz distance is maybe 1.2 kilometers, also low data rate. If we increase the data rate, the distance will actually go down and we will maybe have 100 meters. And 2.4 gigahertz signal, you know, maybe we get 200 meters if we're lucky, but also not big range. However, the cell phone wireless communication gets much higher distances. So for example, this LTE communication, we can check out somewhere here is also their frequencies and distances, but generally, you know, that cell phone, oh, here's the frequency bands, you can check out them, from 600 to 2.6 gigahertz, from 600 megahertz to, for example, 2.6 gigahertz. So, you know, frequency is approximately in the same range. And as you know, cellular signal travels high distances and is high speed. So how is it possible at high frequency? So for example, you know, cellular signal is from 600 megahertz to 2.6 gigahertz. And the only way they can achieve high range of several kilometers is if they use a very loud and very strong signal. So cellular operators pay a license fee, and if they pay it, they get the rights to transmit at powers up to 2 watts. Okay, so we normal people can only transmit up to 100 milliwatt strong signal, but cellular operators, because they pay license fee, they get to transmit at up to 2 watts of energy, of power, right? So you can use these frequencies without license. You're free to use them, but you have to be silent. And if you pay, then you can transmit at much higher energy. So 2 watts was for 2G. And actually, the problem with this high power signal is that it drains battery pretty quickly. So for example, if you have a device that works at 868 megahertz, it's 25 milliwatts. This thing, 2 watts, is 100 times louder signal. But even though you get 100 times longer range, the problem is that the battery would drain very quickly. So to reduce the battery drain, to make the battery last longer, the new LTE 4G signal in cellular networks actually only transmit at 0.6 watts maximum. So actually, if you believe that 5G causes cancer, then you would have to believe that 2G causes 4 times more cancer, because actually the new 4G and 5G signals are actually weaker than the old 2G signal from 1990s. So if you want to protest against 5G, you should first protest against 2G. 2G is still supported by cellular networks for backward compatibility with older phones and with older telemetry devices, right? So even though we receive more and more Gs in our cell phones, you know, the newest cell phones have 4G or 5G, the cell phones and the towers still use also 2G for backward compatibility. Uh, So, you know, you would want to switch off this 2G network first before you attack the 5G, because power is so much smaller. So that is about the powers. So if you don't want to buy a license, you transmit at low powers. If you buy the license, you can transmit louder at some certain frequencies. And the frequencies are in, for example, this Wikipedia article. You know, you can transmit at 600, 750, and so on, if you pay the money, if you buy the license. Okay. That is about the transmit power. Higher transmit power means longer range because the signal is louder, but it also means shorter battery life, right? That's common sense. Next up, the next property of the wireless signal is, let's see, data rate. Wait, before we talk about data rate, we need to talk about these magical decibels. In radio, uh, in radio area, these milliwatts are not that often used. Actually, decibels are used much more often. What is a decibel? Decibel itself is a ratio between some fixed signal and your signal. And in case of dBm, the fixed signal is just 1 milliwatt, is 0.001 watt. And the formula to calculate decibels, you can also find it on the internet, it's not a secret. So here's also a lookup table for decibels power ratio. So why use decibels? First of all, why would you want to use decibels instead of milliwatts? So the reason to use decibels is the following. When you transmit signal, you have a transmit power of, for example, I don't know, let's take this case, 10 milliwatts. You transmit 10 milliwatts. The problem is when your signal travels through air, it travels to all sides. So the further away from your transmitter the signal is, the weaker it gets because it's spread across a wider area. So, and also if it goes through walls, it loses some energy during the penetration of the material. So actually, after this signal goes and travels through air and through walls, the receiver can hear, for example, 0.00000000000000001 watt, right? And you can believe me or not, but the modern receivers actually can hear these silent signals. So you send out 10 milliwatts, which is 0.001 watt, sorry, 0.01 watt. But as it travels through air and walls, the receiver only hears, for example, 1,000,000 times more silent signal, or 1,000,000,000 times more silent signal, weaker signal. So in order to kind of avoid writing these hundreds of zeros or tens of zeros, people use decibel scale, because, for example, in this lookup table, we can see that, for example, 0.00000000001 as a fraction can just be written as minus 100 dBm, minus 100 dB. So we just can write very small signals in shorter manner, and also very loud signals. For example, 10 billion times stronger signal than 1 watt can just be written as 100 dB, right? So dB is used to write very big and very small numbers in a more convenient way. So, and in radio frequencies from olden days, we use ratio relative to 1 milliwatt. And so the formula is the following. Power in milliwatts is power in dB, LP apparently it is 10 times logarithm of base 10 to the ratio of your signal against the reference signal. It looks complicated, but it's actually very easy. It tells you what power of 10 should you use to describe your signal relative to 1 milliwatt, or since the base is 10, it just tells you how many zeros you want to put. So LP is 10 times logarithm with base 10 of your signal power against reference power 0, which is in our case for radio frequency, guys, it is 1 milliwatt or 0.001 watt. And let's just try to convert some numbers. So let's convert 10 milliwatts to dBm. You know, it's actually pretty simple if you start calculating it. So 10 milliwatts is equal to 10 times logarithm of, with base 10, of ratio 10 milliwatts, our signal power against 1 milliwatt. And let's try to calculate it. It's 10 times logarithm with base 10 to 10 divided by 1 is basically 10. 10 divided by 1 is 10. So it's 10 times logarithm with base 10 of a number 10. And what is logarithm? Logarithm tells you to what power should you raise 10 to get 10. So if we say a to the power of b is equal to c, then b is logarithm with base a to c, right? Something like that. And in our case, a is equal to 10. So 10 to the power of b is equal to c, and we need to find what b value is. So how to write it more properly? Log. So b, the result is logarithm of 10 to our number 10. So in what power should you raise 10 to get 10? Actually, it is just 1. The answer is 1 because 10 to the power of 1 is 10. So logarithm of 10 for base 10 is 1. So actually this part is equal to 1. And we get 10 times 1 is just 10 d bm. So 10 milliwatts happens to be 10 dBm. Okay, let's now calculate 25 milliwatts. I'll erase this thing. So 10 milliwatts is totally the same thing as 10 dBm. Next is 25 milliwatts. So it's 10 times logarithm with base 10 of 25 divided by 1 milliwatt. And since it's relative to 1 milliwatt, then we can write it. So what is the exponent of 10 to get 25? It is not going to be a beautiful number. For example, if it's 1, 10, or 100, then it's a round number. But in our case, it's not going to be a beautiful number. So we just take a calculator, we select scientific, and so we want to know what's the logarithm of base 10 to 25. We write 25, and here I wonder how I can get more functions. I think that this log is logarithm of base 10. Yes. So if I write 25 and press log, it calculates logarithm of base 10 to number 25. And the answer is 1.39794 blah, blah, blah. Long number. So it's 10 times 1.4. It's approximately 1.4 is equal to 14 dBm. Okay, and the third 2.4 gigahertz, 100 milliwatts, you can calculate in your head. 10 times logarithm of 10 for number 100. To get 100, you have to square number 10. So the answer is 2. So it is 10 times 2 is 20 dBm. So it can actually be calculated using a calculator to convert from milliwatts to dBms. There are just some values that if you work a lot with the radio, you can just, remember. For example, 10 milliwatts is 10 dBm, 25 milliwatts is 14 dBm, approximately, not precisely. This number was not beautiful. It was 1.397 and so on, but approximately 14 dBm. And 100 milliwatts is 20 dBm. Or you can also use online calculator, milliwatt to dBm. there's nothing bad in calculating it with calculator. So you want to enter power in milliwatts, for example, 25 milliwatts, and you press convert, and it tells you it's 13.979 dBm, which is approximately 14 dBm. Okay, and you can also calculate it in the opposite way. So so the reason to use a logarithm and to use these dBms is the following. We can go online and find some radio chips, for example, Silicon Labs, SI 4463. You know, I just know this because we worked with it in our work, and it has some information. For example, maximum output power from -20 to 20 dBm. Okay, so it's 20 dBm. You can go out to this table. 20 dBm is 100 milliwatts, so it's pretty powerful. But you can set it to -20 dBm if you want to. Using this conversion tool, we want to convert dBm to milliwatts. So it says -20 dBm. -20 dBm is 0.01 milliwatts. So we know that we have a range of 0.01 milliwatts to 100 milliwatts. But what is more interesting for these dBm things is, if we go to datasheet, let's see, it also has information about sensitivity or reception dBm. So it says receive sensitivity is -126 dBm. So it tells you how a silent signal it hears. So you transmit it, for example, at 10 milliwatts. What is -126 dBm? If we can convert it with some tool, so instead of milliwatts to dBm, do the opposite, dBm to milliwatt converter. So -126 dBm is so I'll copy this number. So that chip is able to hear signals which have power, well, actually not power, but the power that enters antenna is just 2.5 times 10 to the power of -13, which is basically 0 point and then 12 zeros, and then 250 or 25, something like this. This is the milliwatts that antenna receives. So you send out, for example, 100 milliwatts or 25 milliwatts, doesn't matter. After traveling through air and through walls, antenna only hears a small fraction of the original signal. It hears it very quietly, but if it's higher than the remaining power is higher than this little power, it can hear it. So it's milli, micro, nano, pico, femto, 250 femto watts of energy. So, you know, the receiver is really, really good if it hears these silent signals. So, but because people didn't want to type inside this datasheet 0.000000000025, they just wrote it in decibels because it's shorter, -126 dBm. And also for other purposes, dBm is a little bit better. So if, for example, you lose half of energy, dBm goes down by 3. It's one way to remember some shortcut formula. So that's about dBm. So you can express things in milliwatts or in dBm. If you want, you can just memorize some very popular dBm values like 10 dBm. So 1 milliwatt, for example, is 0 dBm. 0 dBm is 1 milliwatt, you know, and some other values. And yeah. And that will be all for today. So if you have some questions, you can type them in the chat. If not, then we meet on next week, I guess. So the next lesson we have, let's see, calendar. So next week we have 2 lessons on Tuesday. One is the lab, where you would arrive at 10:15, and we would do some programming in school. And later the same day at 2:30, we have a similar lecture to this, and we continue talking about radio signal properties. So this video, after we close this video, it will be saved to my computer, and I will upload it to Ortus probably within a few days, because maybe I have to cut the beginning of the video and the end of the video, you know, to cut off some silence or some introduction that is, you know, irrelevant. And yes, these will be on Ortus. And I'll try to put some tests on Ortus for you to fill so that you can start earning your mark for this subject. Okay, so I will stop sharing the screen. Also,